During the Second World War, dozens of unconventional vehicles were developed in Germany. Some of them were brought to production, while others remained at the level of prototypes or isolated tests. After the end of the war, many such projects were abandoned. Equipment rusted at proving grounds, was kept in closed bunkers, or simply disappeared from reports. Among them were super-heavy machines, both finished and unfinished, unusual transport solutions, single-use devices, and designs with atypical layouts. Some looked like a technical experiment, others like an attempt to urgently address a specific military task. For a long time, they were known only through archival documents. Later, some specimens were discovered, restored, or studied in detail using blueprints. Why did they appear? What tasks were they supposed to solve? In this episode, we will examine 5 such projects, strange and controversial, and in some cases, quite successful. At the beginning of the war, the German command proceeded from the idea of quickly moving large formations with heavy weaponry by air. This was not about dropping light infantry, but about transporting artillery, vehicles, and even medium tanks without disassembly. Experience from aerial operations in the Netherlands and Crete showed that gliders allow for the delivery of equipment more accurately and compactly than a parachute drop. However, existing models had limited payload capacity. In the year 40, a requirement was formed to create a super-heavy glider capable of carrying up to 20 tons of cargo. Thus appeared the Me-321, a huge transport glider with a wingspan of more than 50 meters. It could indeed lift heavy equipment, but operation revealed serious limitations. For takeoff, a combination of several tow planes was required. In addition, landing a fully loaded glider required a long, prepared strip and precise calculation. By the year 41, it became obvious that the concept of a super-heavy glider without its own engine was too dependent on external factors. Simultaneously, Germany faced growing logistical difficulties. The Eastern Front stretched for 1,000 kilometers. Supplying the North African group was complicated by the actions of the enemy fleet and aviation. A need arose for a large transport aircraft capable of taking off independently, carrying heavy cargo, and operating without a complex towing scheme. The solution proved obvious: to turn the Me-321 from a glider into a powered aircraft. It was from this task that the Me-323 Gigant grew. The fuselage retained its characteristic rectangular cross-section. It was wide and high so that wheeled vehicles could be driven inside without disassembly. In the nose section, large double-leaf cargo doors were located, opening to the sides. This allowed for the loading of cars, guns, and even light tanks directly from the ground. The wingspan exceeded 50 meters, making the aircraft comparable in size to the 4-engine strategic bombers of the Allies. However, the Gigant was wider and more massive in its fuselage. The maximum takeoff weight exceeded 40 tons. The wing structure was reinforced to withstand the additional load from the power plant. Production versions received 6 piston engines of French manufacture, placed 3 on each wing. Each engine developed a power of about 1,000 horsepower. This solution was dictated by a shortage of more powerful German engines and the need to use available captured production facilities. The landing gear was a multi-wheel system with a large number of struts. It was intended to distribute the load across dirt airfields, as by no means all strips at the front had a concrete surface. Despite this, operation from unprepared sites remained difficult. The payload depended on the modification and flight range, but on average, the aircraft could carry about 12 tons of cargo or more than 100 fully equipped soldiers. At the same time, the maximum speed was approximately 270 kilometers per hour. The cruising speed was even lower. In conditions of enemy fighter superiority in the air, this made the aircraft vulnerable. Armament was gradually strengthened. On late versions, several defensive machine guns were installed in the upper and side positions. However, it was impossible to fully protect such a large and slow aircraft from fighter attacks. In terms of its dimensions and cargo capabilities, the Me-323 became one of the largest production transport aircraft of its time. But its size was simultaneously its main advantage and its primary problem. The main burden on the Messerschmitt Me-323 Gigant fell on the supply of German troops in North Africa. After the reinforcement of the grouping in Tunisia and the deterioration of the situation at sea, Germany increasingly resorted to air transport of heavy loads. Gigants moved artillery, vehicles, ammunition, and personnel across the Mediterranean Sea. It was in this region that both the capabilities and vulnerabilities of the aircraft were manifested. On the one hand, it allowed for the delivery in one flight of a volume of cargo for which several smaller machines were previously required. This sped up the transfer of equipment and reduced dependence on sea convoys. On the other hand, the low speed and huge dimensions made it a convenient target for Allied fighters. An episode is known in the spring of the year 43, when a group of Me-323 was intercepted and almost completely destroyed in the air. Losses were heavy. Along with the aircraft, crews and the transported cargo perished. For transport aviation, this meant not only material damage, but also the disruption of supply in specific sectors of the front. On the Eastern Front, Gigants were used to transport equipment and evacuate the wounded. However, the length of the routes and the limited number of machines did not allow for a radical change in the logistical situation. The aircraft required significant technical maintenance, and spare parts were becoming fewer and fewer. In addition, operations showed that 6 engines complicate maintenance and increase fuel consumption. In conditions of a growing shortage of resources, this became a serious factor. Each loss was sensitive, as the production of such large machines required significant materials and time. In total, just over 200 copies of various modifications were built. Some were destroyed in combat conditions, some at airfields as a result of bombing. By the end of the war, the use of Gigants decreased due to a lack of fuel and the general deterioration of the situation in the air. Sonderkraftfahrzeug II Kettenkrad appeared as an answer to the problem of mobility for light units in conditions of heavy off-road terrain. In the first years of the war, German units actively used motorcycles with sidecars for communication, reconnaissance, and the transport of light loads. On solid roads, they were fast and convenient, but on the Eastern Front, the situation changed. Autumn mud, deep mire, snow, and the absence of a normal surface sharply reduced the effectiveness of wheeled vehicles. The command required a compact machine that would combine the speed of a motorcycle and the cross-country capability of tracked equipment. At the same time, it had to remain light so that it could be transported by air and used in paratrooper operations. In the year 40, the firm NSU Motorenwerke was tasked with developing a light half-track tractor. The technical assignment specified the need for towing light anti-tank guns, transporting ammunition, and use as a means of communication. The possibility of operation in conditions of limited production resources was also taken into account. The result was an unusual hybrid of a motorcycle and a tracked machine. Formally, it was classified as a small half-track tractor, but externally it more closely resembled a motorcycle with a tracked rear part. Sonderkraftfahrzeug II Kettenkrad was a compact machine with a combined steering scheme. In the front part was a standard motorcycle wheel with a fork and handlebars. Behind the driver was a tracked block with 2 drive wheels and a system of road wheels. The main feature was the steering system. On solid surfaces, the machine could be steered by turning the front wheel like a motorcycle. However, on rough terrain, the transmission played the main role. When turning, a mechanism for braking one of the tracks was engaged. This allowed the machine to be turned even in limited space. The engine was of an automotive type, a 4-cylinder liquid-cooled unit. Its power was about 36 horsepower. The gearbox had several speeds forward and 1 in reverse. The maximum speed on the highway reached approximately 70 kilometers per hour, which was considered a high figure for tracked equipment. The mass of the machine was just over 1 ton. The crew consisted of a driver and up to 2 passengers on the rear seat. The payload allowed for the transport of ammunition or light equipment. In addition, the Kettenkrad could tow a trailer or a light anti-tank gun. The design was relatively compact, which allowed for the transport of the machine inside transport aircraft and gliders. This corresponded to the original task of using the equipment in paratrooper operations and in conditions of limited infrastructure. However, the combination of a motorcycle steering part and a tracked drive complicated maintenance. The transmission was more complex than that of a standard motorcycle, and repairs in field conditions required preparation. Sonderkraftfahrzeug 2 Kettenkrad was used in various sectors of the front and in different climatic conditions. On the Eastern Front, it was used as a means of communication and a tractor for light anti-tank guns. Thanks to the tracked drive, the machine maintained cross-country capability in mud and snow where ordinary motorcycles got stuck. This made it useful during periods of mud. In North Africa, the Kettenkrad was used for transporting cargo and servicing units in conditions of sandy soil. The low mass and sufficient towing power allowed the machine to move over loose surfaces, although engine overheating and the wear of components in the hot climate remained a problem. A separate direction of use was airfields. The Kettenkrad was used for towing fighters and light aircraft along dirt strips. The narrow track and compact dimensions made it convenient for maneuvering between parking spots. In this capacity, the machine proved practical and received widespread use. In total, several thousand units were produced. This made the Kettenkrad more mass-produced than many experimental models of equipment of that time. However, it did not fully replace motorcycles and light trucks. The reason was the complexity of the design and higher cost compared to standard wheeled equipment. Operation required training. The driver had to take into account the features of the transmission and the turning mechanism. With incorrect use, the wear of tracks and elements of the braking system increased. After the war, some of the machines continued to be used in agriculture and forestry. The tracked drive proved useful when working on soft soil. Nevertheless, as a military concept, the Kettenkrad remained a specialized solution for specific tasks rather than a universal machine. Goliath, officially a light carrier of an explosive charge on a tracked chassis, appeared as an attempt to solve the task of destroying fortified targets without direct contact between infantry and the enemy. By the beginning of the war, it became obvious that attacking long-term firing points, barricades, and tanks in urban areas leads to high losses. A means was required that would allow a powerful charge to be delivered to the target remotely. In the years 39 and 40, German engineers studied various methods of controlled explosive devices. Both radio-controlled schemes and wired systems were considered. Radio control was considered promising, but in conditions of active interference and a lack of reliable equipment, it was unstable. Therefore, it was decided to use wired control. The development was entrusted to the firm Borgward. The concept consisted of creating a compact tracked machine for single use, inside which an explosive charge was placed. An operator controlled the device from cover via a cable several hundred meters long. After being guided to the target, the mine was detonated. Thus appeared the Goliath, one of the most unusual examples of remotely controlled weapons of the Second World War. Goliath was a small tracked machine with a low profile. The height of the hull was less than half a meter, which allowed it to partially hide behind terrain irregularities. Inside was placed an explosive charge with a mass of 60 to 100 kilograms depending on the modification. This was sufficient for destroying a fortified firing point or seriously damaging a tank. Early versions were equipped with an electric motor and powered by batteries. Control was carried out via a 3-core cable approximately 650 meters long. The cable unwound from a reel in the rear part of the hull as it moved. The operator controlled the direction and speed with a remote while staying in cover. Later, a version with a gasoline engine appeared. It had a greater range and a simpler power system, but remained vulnerable to mechanical damage. Regardless of the variant, armor protection was minimal. The hull protected only from small fragments and small arms fire at long distances. The speed of movement was about 10 kilometers per hour. Maneuverability was provided by separate control of the tracks. However, if the cable was damaged, control was completely lost. This was one of the main vulnerabilities of the system. The mass of the device exceeded 300 kilograms. Transport to the front line required the efforts of the crew. Despite its compactness, the Goliath was not light to carry. Such devices were most actively used on the Eastern Front, as well as during battles in Italy and the defense of France after the Allied landings. Theoretically, the concept looked rational. An operator from cover directs the tracked machine to the target, brings it close, and carries out the detonation. This allowed a sapper to avoid going out directly under enemy fire. However, in practice, many problems arose. The main vulnerability lay in the control cable. It could be severed by fragments, a bullet, or simply cut. In urban combat conditions, the wire often got caught on obstacles. Loss of the cable meant loss of control. In addition, the Goliath itself was slow and noticeable in open terrain. The enemy quickly understood the principle of operation and began to purposefully destroy such machines with small arms fire. The electric version suffered from limited battery life and high production cost. The gasoline version was cheaper, but the engine noise made it more noticeable. At the same time, armor protection remained minimal. Despite this, several thousand units were produced. The mass production was explained by the relatively simple design and an attempt to compensate for the shortage of manpower with technical means. In individual cases, the Goliath indeed allowed for the destruction of a fortified position without direct losses among the crew. However, overall, the effectiveness proved lower than expected. After the war, similar systems were considered an early form of remotely controlled combat vehicles. The concept did not disappear, but received development in more advanced radio-controlled and later electronic systems. The Volkswagen Schwimmwagen appeared as a development of the idea of a universal light military car capable of operating not only on roads, but also on water. Experience from the first campaigns showed that motorized units constantly face the need to cross rivers and canals. The use of pontoons and bridges required time, and in conditions of a rapid offensive, this reduced the pace of operations. The basis for the project was the Army version of the light car Volkswagen Type 82, known as the Kübelwagen. Designers sought to maintain simplicity and the unification of components to facilitate production and maintenance. At the same time, it was necessary to give the machine a waterproof hull and ensure movement on water without complex additional means. Development was carried out under the leadership of Ferdinand Porsche. The task consisted of creating a compact amphibious car for reconnaissance, communication, and the transport of small groups of soldiers. The machine had to be light, cheap to produce, and capable of overcoming small water obstacles without preliminary preparation. The result was the Volkswagen Schwimmwagen, one of the most mass-produced amphibious cars of the Second World War. The Volkswagen Schwimmwagen had a waterproof monocoque body of a boat type. The lower part of the hull was welded and performed the function of a floating pontoon. Unlike an ordinary car, the bottom was completely closed to ensure water resistance. The engine was located in the rear part, as with the base Kübelwagen. This was a four-cylinder gasoline air-cooled engine with a power of about 25 horsepower. Drive was carried out to the rear wheels. Late versions received an engageable drive to the front axle, which improved cross-country capability on difficult terrain. For movement on water, a folding propeller was used. Before entering the water, the driver lowered the propeller manually, and it connected to the transmission. Steering on water was carried out by turning the front wheels, which acted as a kind of rudder. The maximum speed on land reached approximately 80 kilometers per hour. On water, about 10 kilometers per hour. The mass of the machine was less than 1 ton. The crew consisted of a driver and up to 3 passengers. Compact dimensions allowed the car to be used for reconnaissance and communication. Production of the Schwimmwagen began in the year 42. In total, more than 14,000 units were produced, making it the most mass-produced amphibious car of that period. The ability to independently overcome small rivers, canals, and flooded areas gave a tactical advantage in conditions of rapid advancement or when operating in swampy areas. On the Eastern Front, the amphibious qualities of the machine proved useful during spring floods and when crossing shallow water obstacles. In North Africa, the Schwimmwagen was used as a light reconnaissance car, although its amphibious function was used less frequently there. Despite its versatility, the machine had limitations. The low engine power and light construction did not allow for the transport of heavy weaponry or significant cargo. On open water, the car was sensitive to waves and strong currents. It was intended for calm water obstacles, not for full-scale maritime use. Nevertheless, the Schwimmwagen proved to be one of the most practical, unconventional projects. Simplicity of design, unification with other models, and relatively mass production made it in demand. Unlike many experimental models, it was not a technical dead end. After the war, some of the machines were preserved and continued to be used for civilian purposes. Today, surviving specimens are found in museums and private collections. The Faye 330 was developed as a means of increasing the range of visual observation for submarines. In the conditions of the Atlantic, the main task of the submarine forces was the detection of enemy convoys at the maximum possible distance. However, the height of the boat's conning tower limited the view. Even with the use of binoculars, the visibility radius from the sea surface remained relatively small. A solution was sought in the creation of a simple flying craft that could be quickly deployed on the deck of a submarine and used as an observation post. At the same time, the craft had to be light, compact, not require complex maintenance, and fit into a waterproof container. The development was entrusted to the firm Fock-Achgelis, which specialized in autogyros. Designers proposed a simplified scheme, a tethered autogyro without an engine that rose into the air due to the headwind created by the movement of the submarine. The Faye 330 represented a maximally simplified autogyro. It did not have its own engine and rose into the air due to the auto-rotation of the 3-blade main rotor. The airflow was created by the movement of the submarine on the surface. The design consisted of a light metal frame, a pilot's seat, tail fins, and a rotor with a diameter of about 7 meters. Behind the pilot's back was a keel with a stabilizer that provided directional stability. The craft was connected to the submarine by a cable approximately 150 meters long. A telephone cable also passed through this same cable for communication between the observer and the boat's crew. At a boat speed of about 30 kilometers per hour, the autogyro could rise to a height of up to 120 meters. From such a height, the visual observation radius significantly increased compared to the view from the conning tower. Theoretically, this allowed for the earlier detection of enemy ships or the coastline. The mass of the craft was relatively small, which allowed it to be stored disassembled in a waterproof cylindrical container on the deck. Deployment took a few minutes in calm weather. However, operation depended on the state of the sea. Waves, strong wind, and the need to maintain movement on the surface made use risky. In the event of a sudden threat, the boat required time to fold the craft. Otherwise, the observer was vulnerable. The Faye 330 was used limitedly, mainly on submarines operating in remote areas where the air threat was considered lower. The craft was used for scanning the horizon and detecting ships at a greater distance than the tower height allowed. In theory, this gave the boat additional time to make a decision to intercept or, conversely, to avoid contact. However, practical use proved difficult. To lift the autogyro, the boat had to travel on the surface at a constant speed. This increased the risk of detection by enemy aviation. In conditions of growing Allied air superiority in the Atlantic, staying on the surface became increasingly dangerous. In addition, weather conditions limited use. Even moderate waves complicated launch and landing. In the event of an emergency dive, time was needed to put the craft away. If the situation developed quickly, the autogyro had to be detached and lost. In total, a limited number of such devices were produced. They did not achieve mass distribution. As radar equipment strengthened and aerial patrolling developed, the need for such a visual method of reconnaissance decreased.